Hello everyone, video 2 of module 6. In this video I show you how to use table and how to use modal response for normalizing your earthquake load, and also a little bit about what I've done in the last model, some tweaks, and show you the internal forces a little bit in more detail. So let's start about the changes. If you remember, we had some issue about the vertical displacement around the lift. The reason was the shell were not connected to the wall properly. So they were meshed, but they were not edge constrained. Always my suggestion is use the edge constraint for vertical and horizontal shell elements. Even if the joints are exactly matched, my suggestion is do it. There is no harm for that. But definitely that can help you to ensure the compatibility of the formation and transferring load properly to the wall. Because the shell were not connected to the wall properly, the load wouldn't be transferred to the wall, so we had very small loads on the lift core. That's why we had very small loads on the pile of the lift core foundation. Also here the shell was not divided where the wall was, so I divided the shell to two segments at the left and right, and then auto mesh it. I also add some joints to all beams and auto mesh the whole shell. So few stages you always need to follow before running your model. First, press Ctrl A, select all joints and merge the joints with a reasonable tolerance, for example 20 millimeter. Second one, select all frames and joints. If they are not braced like that, then use auto mesh for frame. If you have some braces, you don't want to connect them together, you need to exclude them from your selection. The next stage is selecting all joints and also all shells and auto mesh the shell, but you need to see which option is suitable for you. And the last stage is selecting all vertical and horizontal shells and do edge constraint. If you do these 4 stages, generally something around 70 to 80% of the issues you have in the analysis will go. But you always need to review the model. You need to ensure the load is being transferred properly. There is no issue with regards to transferring load and compatibility of the formation. Those two are the key. SAP doesn't show any error, but again, the model may not be completely right for your design. So let's have a look at the frame. At this area you can see this is modal displacement. Let's show you the vertical displacement. So I'm coming to BUG2, doesn't matter, it's ultimate. This is not the combination you need to choose for checking the displacement. I'm just showing, so you can see here that the actually displacement is correct. Now I can start the animation. You see all of them are moving together, so that is correct. If I have a look at the internal forces here for these piles, now you see these piles are taking even more load. So here is 1650, here is 1850, and it's normal because yes, you don't have a little bit shell in the void area of the lift, but you have the lift wall weight which is heavier than other areas. So logically here you should have more load. Moreover, you have a higher wall for the lift pit and a bigger foundation and pile cap for the lift pit. So this pile should take more load than the other piles. Now it sounds correct. This is again is correct because part of load is being transferred to the wall. Now let's have a look at ground floor slab. If you remember, we didn't have those joints on the frame, so the shell was not auto meshed properly, and the load from shell to beam wouldn't be transferred correctly. Now we've done all of them. Let's have a look at this shell in more detail. So I'm just selecting all of them, show selection only, and I will make it 3D. just zoom in a little bit. Okay, so let's see what we have here. So if I come to shell and I choose M11, if you remember, M11 was the moment along grid 1, not based on right hand rules. So if I show you local axis here for shells, you can see the red axis is in this way. So this is axis 1. Let me zoom a little bit more. So the green is axis 2 and blue is axis 3. So when I show M11, it's showing the negative and positive moment change along axis 1, not based on right hand rules, as I said. So let's have a look. So you can see here moment is negative on top of the beam and then coming to positive and again negative. If I zoom out a little bit, you will see the contour is not very clear because the range of the moment is from 630 kilonewton meter to minus 280 kilonewton meter. But you don't have such a range here. You need to limit the range to make the color more clear for yourself. So if you come here and use user defined contour, you see the range here is from minus 19, some areas up to minus 30, and here is something around 20. So if I show a range here, for example, minus 20 to plus 20, I intentionally make it a little bit less to tell you what I'm after here. So plus 10, you can see the contour change and you have more range of colors here. But you see some areas are solid color. So whatever is more than absolute value of moment is just purple. The numbers are more than 10 kilonewton meter are blue. So this is how you can figure out if, for example, the moment capacity of the slab based on your reinforcement arrangement is a certain amount. You can put the range here and you can see easily what areas are overstressed and where you need to add some extra reinforcement. So if I change this contour, for example, to minus 50 and plus 20, that almost covered the whole range we have. Now you see less solid color areas. Still you have an area more than 20 kilonewton meter per meter, and area which is the absolute value of negative moment is more than 50 kilonewton meter per meter. So that's how you can use this and figure out the areas that are overstressed. The other direction, if I show you, you will see the same. Now the moment is in this way, negative and positive. So this is along grid 2. And you can do the same for shear and for internal forces if you want to see. That shows the shear is not that much, so you can play with this deform contour range again. Again, the same for shell stress. You can do the same. And as I said, if you show the envelope, then you have here envelope max and envelope mean. So you can choose you want to see the maximum range or minimum range. So if I apply here the maximum range, generally it takes a little bit time because this envelope of all loads, you can see all positive values or the smallest negative values for each combination for each area is showing. But if I go to envelope mean and click on the same area, instead of minus 9 or minus 10, you will see minus 21. That means this is the maximum actually absolute value of negative moment that you can see here. So this is generally for contours. I would like to share in more detail because last video we didn't have a chance to do that. And now let's show you how you can use table. So if you come here in display, you can go to show tables, and in tables you can choose different outputs, and that will be shown in a tabulated format. So If, for example, come to system data, is nothing special, mainly showing the coordination and control data. So there is not much information here for you. Those are property definitions. You may want to check, for example, your area section properties. So you can select here, have you defined your section property for design parameters? Not yet. So we're just showing the section properties. I leave this one later in our next series of video in module 6 for design. And for example, rebar sizes or anything you want. When you press OK here, then you can see, for example, 160 slab is shell thin, and then thicknesses. And if you move here, you can see the other information that you have. Any modification factor you applied, all of them can be checked. You select a couple of items, so you can come to this drop box, for example, check rebar sizes, and it shows you all rebar sizes you have. That we haven't gone through this yet, we haven't used it, and you can even add rebar sizes if you want, if there is any standard size that you need and it's not here, for example 22 millimeter or 24 millimeter diameter or 30 millimeter or more than 30 millimeter, you can add them here. So let's back again and show you some other options. So this is for property definition. Then you have load pattern definition. So in load pattern definition, you have load patterns, autoseismic load. So those are the things that you generally want to check. For example, autoseismic load, you want to ensure about the eccentricities, about the factor of earthquake applied. So if you press here, and it's coming here, so this is autoseismic load. You can see the eccentricities for positive and negative are applied correctly, and direction of x and y is correct. And then you coming here, C factor is 10%. All of them are shown. Even because the model is run, you can see the weight of a structure participating in earthquake and the base shear according to this weight. So this is 10% of the total weight participated in earthquake. That will be defined based on the mass source we discussed last time. So you can add tables here. You don't have to close and open it again. Now I want to show you where you can find load combination, because it's not very clear. If you come to load pattern definitions, there is an option here named response combinations. If you click on that, you can see combination definitions. So if I click on this and add to my tables, then you can come here, you can see combination definitions. You can find it in Dropbox if it's not showing at the beginning. Then you can see here all load combinations I've created. And there is a great facility in SAP that you can export this table to Excel, edit it in Excel, and again put it back. There are few options like live model, that automatically model will be updated based on updating the Excel. Actually, what I've done to create all those load combinations, I use this option, and you can come here to file, go to export, and export the whole model to Excel file, a spreadsheet, and then edit it and again import it. Or just for few options in the table you can do the same, but this is for advanced course, not for a preliminary course, so I'm not going through all those details. I'm just telling you that there is such a facility and great user interface is available. And the other options you have here about load case definitions, for example, here you can see the factors you applied for a static load case and modal load case, all of them. You can come here and select the load cases you want to see. So if I come here, for example, select dead and displacement, by press Ctrl you can select multiple of the load cases. So you can choose all those individual load cases, and then you can press OK. Window is remaining still. You can press OK, and whatever you chose here, it's going to this table. So if I come here and go to load case definitions, now I can see all load cases that I selected and what are the specifications of them. So if for example p delta is non-linear, it's mentioned here non-linear static, there star linear static. If there is an initial condition that for earthquake we use p delta, so they started from p delta stage. So all of them are clear here. You can double check, ensure nothing is missed. If I back here again, so the rest you can have a look about the assignment of the frames and joints and area, option preferences. Here in miscellaneous you can see some basic information or material list. Then if you run the model, you have the information of the analysis as well. So here you can come here, for example, joint output, element output, run information, and the summary of the run. And here in the structural output you can see other information, for example base reaction. And if I press here base reaction, then I need to come here and select the right load case. For example, if I come here and say I just need these 4 and press OK, then when I'm coming here I can go to base reaction, which is here. So this is not in order of the menu, you see this is based on alphabetical order. So if you come here you can see the base reaction, which this number is 5423 is the same as autoseismic load. So if I come to autoseismic user coefficient, you can see 5423 here. So that's how it works.